Good afternoon, everyone. Welcome to the Industrial Talk Series co-organized by IEEE YP and Singapore and NTU IEEE GSC. I'm Jovin, the president of the IEEE GSC. Welcome. Please accept our warm welcome to this seminar about wireless communication design constraints in automotive applications. First of all, please allow me to introduce about our keynote speaker, Mr. Fernandes. Fernandes has been working in radio frequency design, wireless technology, high-speed laser communications, RF system design, and R&D innovation for over 25 years. With extensive knowledge and experience in the product development industry, and participant in over 20 development projects worldwide with 28 patents released and 3 patents pending and 10 years of leadership experience leading a diverse team of cross-location RF designers working with suppliers to meet the project requirements for new developments in automotive and industrial applications. So before the seminar starts, please let me give a notice for those who have joined online. If you are the IEEE postgraduate students who needs seminar attendance endorsements, please ensure that your username has been displayed as your student email here, and at least 18% of the duration is compulsory for the endorsement. Now let's welcome Mr. Fernandes for the speech.
Yeah, thank you for joining today, and thank you to Jovin for the introduction. So today what I would be presenting is wireless communication design constraints in automotive applications. So typically, as part of your bachelor engineering programs, you do a lot of technical information and a lot of maths, maybe, and a lot of analysis, understanding of theory. A lot of times what happens then when you move from engineering into the industry, there's a lot of practical applications. There's a lot of constraints. There's a lot of, in a sense, you need to balance between performance and utility. And sometimes there's a lot of constraints that you see. And when you talk about the automotive application world, then you have automotive constraints that you would see in the automotive world. So before I start, I'd really like to right. I'd like to thank the IEEE Young Professionals Singapore and the NTU IEEE Graduate Students Club for inviting me to speak here, and also Dr. Shawan for introducing me here, and also thank you to Prof. Kwan for joining as well. So nice to have you here. Yeah, so as an alumni of NTU and also a member of the IEEE, it is really sort of pleasure for me to give back to this community. Yeah, so to also share with you my experiences from the industry, my experiences from what I've seen in the past 25 years. Yeah. So yeah, I think this is the location. So it was a bit of a maze. NTU is always a maze. So I finally found the place. So the training or the presentation today, I would cover primarily two sections. The objective here is to give you an overview of what we have in the automotive world today, so that then you can understand what we're talking about in terms of constraints. And then, of course, I'll do a short recap. I only have 45 minutes to present today, and then maybe 15 minutes to for Q&A if you have anything. But of course, during the talk, if you have any questions and you want to interrupt, please feel free to raise your hand and let me know. Yeah. So wireless communication technologies and techniques are essentially the enablers of new functions, new innovations in the automotive world as we see today. And we are seeing, or at least now I will present some of the newest innovations that we have, like vehicle access sensing, radar, child protection, detection features. And these are features that we are implementing into our customer vehicles for the future, what we call OEMs, or original equipment manufacturers. They are essentially the manufacturers of the vehicles. Typically, wireless communication brought to prominence the need for mobility and self-organizing networks. So you remove the wire from any application and you improve significantly the utility of your product. But of course, you have to have the ability to communicate wirelessly in the network. Of course, wireless communication also forms the backbone of some of the critical infrastructures for systems like safety, datacom, satellite com. And also, as we see in the future as well, that we start to see edge computing coming into the picture. Yeah, so wireless communication would then be the information backend that enables edge computing and edge-based user interface. And then, of course, you see wireless standards organizations worldwide are becoming significantly more active, significantly more critical in terms of defining the functionality. They're becoming important in terms of standardizing functionality across OEMs, across countries, and across features in a sense. Yeah. So first, I give you an overview of what we have in the wireless world, some of the latest gadgets, so to say, in high-end vehicles, and then we look at the constraints. So of course, as I mentioned, without understanding what is the automotive environment, then it's really difficult to understand what constraints we're going to see in the automotive world. So the key thing to understand first is this is a vehicle. So in the automotive world, for example, if you were to do industrial wireless communication in industry, for example, you would be looking at a shop floor or some kind of machines. Yeah. But for us, wireless is implemented inside this vehicle. And this would be what a typical chassis looks like. It's a composition of different metal parts formed differently to ensure probably ability to put speakers. It has to be strong. It has to have maybe a crumple zone in front. These materials could be different. There could be different materials used for strength, different materials for lightness, durability. And these are then welded together at each of these junction points. So they're not going to be perfectly, this is not a unibody construction. Of course, there are new OEMs that are doing unibody constructions, but those are more expensive, significantly more expensive. So typically construction is like this. So you're going to have different metals, different materials, different epsilon R, different conductivity, different connection points. So all of this affects the wireless performance of the vehicle itself. But then, of course, you also have a lot of wiring inside the vehicle. So you've got to get power from the battery to the device, wherever it may be. You need to have headlights powered in. You've got wipers, you've got maybe body controllers, you've got different features, different actuators in the vehicle, different modules, what we call ECUs, all over the vehicle. And this has to be powered using these cables. And you see that typically a vehicle is not grounded to earth, so it is essentially a floating ground. And what this means is that all of the ECUs in the vehicle have to be able to tolerate a certain level of voltage variation, ground variation. And this also means there's going to be a lot of reflections inside the vehicle, current passing from unit to unit. So all of these are part of our robustness requirements for the electrical design of the ECUs in the vehicle, the ability to tolerate these variations. But then this also means that this affects the RF as well. The RF module would be equally subjected to certain conditions like this. So that's what we then build our wireless functions on top of, like communication, sensing, what we call child presence detection. I will explain that later, as well as communication on the highway. Yeah? So here, a critical aspect that we have to keep in mind, the constraint, is that these vehicles are moving at very high speed, and they could be moving at different speeds on the highway, and they've still got to be able to reliably communicate between each other. Yeah, so we have to consider phase differences, Doppler shifting, and things like this. So a lot of constraints on the application side itself. So at Continental, we are working on the future of mobility, wireless communication, software-defined vehicle. This is a new aspect that we are introducing, where all of the features are defined first in software, and then you can choose plug and play what you want to implement on the ECU. Artificial intelligence, open source software, collision warnings, digital guardian, automated driving, and of course, very important now, sustainability. So you can also have a look at the, not sure if I can move this, but no, it's okay. I think it's fine.
Which one is that? Loading meeting control. Oh, this one.
Oh, perfect. So of course, this is our website. You can go here, continental-automotive.com, and you should be able to see our latest news. It's constantly updated. We are currently working in partnerships with Copernicus, AI Labs in Berlin. We're doing collision warning systems for our digital guardian angel. We're working on topics like motor positioning, ultra-wide displays, and yeah, of course, the future of mobility. This is a critical topic. One interesting article would be this, Tech Talk, Psychology of Mobility, would be interesting to read. And we've got numerous awards. IFOY Award in 2023 for some of our designs, the PACE Award for COSMA, and yeah, also later we see some more awards from our German OEMs, the vehicle manufacturers. So what are the products we are? So I'll just give you a brief overview of some of the products that we have. So one of them is digital access solutions. And this is what we call the Continental Smart Access. We use ultra wideband time of flight to make very precise ranging. And we use this then to access the vehicle, to authorize entry into the vehicle, and to authorize engine start and things like this. We also have our intelligent antenna modules. This is a really compact integration of all of the wireless services that we have, and all included in one consolidated package together with the antennas and with all the electronics on board. So typically in the past, it used to be separate units. So if you had 5 or 6 services here, for example, you would have 6 different ECUs with 6 different separate antennas installed, and then of course coaxial wires to connect the two. So what this does is it integrates everything together and gives the car manufacturer one single ECU to install. So it reduces also the installation cost. Yeah, so then we use this to implement V2X, the vehicle-to-vehicle communication for a lot of different features. So we have V2X now defined since release 14 on the LTE network. And we also have vehicle-to-vehicle and vehicle-to-X communication using the 802.11p standard as well. And this is predominantly interesting in, or the interest typically from OEMs are coming in Europe mostly, and CV2X significantly in Asia, China, and regions like this. And therefore, to cater to all of these potential markets, we also have an integrated architecture, in which case you have the possibility to have one product that does both, depending on which region you go to and which application you want to use, which customer wants it. And then, of course, there's the Digital Guardian Angel. This is a feature that provides collision warning systems to warn vulnerable road users of accidents via various notification channels using wireless, probably notifications to the watch, the phone, to the car, to ensure that there is no collisions on the roads. Right, so wireless communication is used in various different ways to communicate between vehicles and the infrastructure of the city, as well as to communicate between the vehicle and maybe cyclists, pedestrians, road users. So we call this typically V2X, but it has a lot of different components in terms of actually using different features, different technologies to communicate between different, in a sense, entities on the road. And then, of course, as we saw before, communication along the highway to inform vehicles at the back of the highway if there are certain road obstructions in the front, in case there's an accident, in case there's a diversion, things like this. So it helps in navigating, but also traffic management to a large extent. But also it's a safety feature to ensure that vehicles are more safe because they know what to expect along the road. And all of this has to be implemented using wireless communication, primarily because you want to have large amounts of data transferred from vehicle to vehicle at precise timings, at precise intervals, and things like that. Similarly here, not only on the highway, but this feature is also relevant inside the cities. This helps in traffic management, especially some of the cities of the future would be really highly densely, there would be a lot of traffic in the cities, and this helps to also mitigate some of this problems. One area that we are working quite importantly in Continental is sensing. And here we use ultra wideband wireless technologies to understand the position of the user and to give a comfort function, what we call a comfort function. For example, when the user is approaching the vehicle in the zone that we call the welcome zone, it can be varied depending on how we define it. But in that zone, the vehicle would then maybe light up, trigger some kind of lighting to allow the user to first identify the vehicle and approach the vehicle. And once the user is within the unlock zone, close to the vehicle, then the vehicle unlocks before the user actually opens the door to ensure that it's seamless entry, for example. Of course, we have to be careful that the precision in positioning is good, because we don't want to unlock the vehicle when the user is far away from the vehicle, which could allow, perhaps an attacker or a thief to steal something from the vehicle, or just steal the vehicle itself, for example. We also have the requirement from some of the OEMs that the user device should be precisely located inside the vehicle before the engine can be started. This to ensure that if the user is outside the vehicle, somebody can't drive the vehicle away, sort of cybersecurity in that sense. So this means that we have to have really precise positioning, not only outside the vehicle, but also inside the vehicle. And that becomes really a constraint, because it's a nice metal cage with a lot of reflections, and then it's really difficult to understand where the signal is coming from. And we do this by having multiple transceivers all around the vehicle. For example, here, 2 inside, 2 on the outside. So this would be a minimum configuration of 6. And if we want to have better coverage at the back of the vehicle and front of the vehicle, later I will explain what coverage means, we would need at least 8 transceivers. And this ensures that the user can be identified precisely outside as well as inside the vehicle. And then, of course, this is a very important requirement in Europe, and will be 100% regulatory required in Europe to have implemented in all of the vehicles. Is something called child presence detection, where we use our existing systems to be able to detect children in case they are left behind in a vehicle, to ensure that a child is not left behind in a vehicle, and it's a safety feature. And we use UWB vehicles to identify micro motions inside the vehicle, to understand using frequency or phase of the signal to understand whether there is even the tiniest motion. For example, the baby is breathing, to identify whether the person inside the vehicle is a child or an adult. And then, of course, we can identify micro body movements, and to give with audible or a visual or a haptic feedback to the user saying that they have left the child behind, or a warning, or perhaps even to start an alarm to ensure that the child is not left behind. And all of this is done using ultra wideband. And in fact, some of the systems that we have done, the proof of concepts, we can also identify in case the baby is covered under blankets, because to ensure that in all conditions, this identification can be done reliably. So it's important, before we go into the constraints, to understand that functions, you can have multiple functions in a product, and each product can have a lot of different functions. But the really unique selling point that we want to provide would be at the intersection of what is a product, what is a function, and what is a technology that is used to implement this function in that product. And this way we have this combination of items coming together, and therefore we can have a single product having multiple functions using different technologies. Similarly, we can have a single technology in multiple products, giving us multiple different functionalities. So it's really critical to understand that all of these 3 things must come together to give us a unique selling point for our customer in terms of the features that we provide. Another important thing to understand, or a topic to understand, is the OSI model. So this always comes up in the sense that when we are talking about wireless communication engineers, we're talking about working on the physical layer. But nevertheless, there's a lot of other layers on top as well. And this is defined in the ISO. And there's a data link layer, the network layer, to provide abstraction between what is happening in different functionalities, between a communication from one node to another, or a computer to a computer. And typically for us, we are working on the physical layer, the actual implementation of the communication between 2 nodes in terms of the wireless propagation. Okay, so now you get a sort of broad perspective of what the automotive environment is. So now we have a quick look at what the constraints are. So in terms of constraints, very important to understand that we are always constrained in every application by the amount of power in the system. So we need to have a certain amount of link budget that we call the difference between the transmit power and the sensitivity of the device to ensure that we can achieve a certain amount of distance. And to have reliably maintain this distance, we need to have an understanding of the amount of power that we have in the transmitter, the cable losses. So in case of a tower like this, the cable, and if you had your power amplifier at the bottom, then the cable losses would be quite high to transfer the power to the antenna. But if it was inside an ECU, then the cable losses would be significantly lower because the distance would be very minimal. Then, of course, you have the antenna gain in the direction of interest. And then, of course, the path loss, so the loss of the signal over the distance traveled. And then we consider as well penetration losses that would occur due to penetrating maybe the walls, depending on the application. So this is all application dependent, but perhaps foliage if it is a large area, or if it is a vehicle to vehicle communication, then penetration losses due to penetration through the vehicle body itself. Then of course we have to consider foliage loss in cases where it's broadcast over a large area, and body block losses due to different bodies along the path of propagation. And this would be all of the losses we would expect. And then we need to also consider some margins. We want to keep some overhead to allow for areas like when we have fading meaning losses that occur due to different effects of the atmosphere or the transmission medium, the slow fading margin, the interference margin due to potential interferers from other devices occurring, so that reduces the signal to noise ratio. And then, of course, very important, rain and ice margin. So we have to consider that we are operating perhaps 24 hours a day. So there's the differences between night and day, whether the sun is directly overhead, whether there's sunspot activity, whether there's rain or ice or storms occurring. All of this would affect the medium of transmission and therefore affect the amount of link or amount of distance that we would be able to achieve. But similarly, we could also consider that the vehicle is the user equipment and the transmission is coming from a tower. Then we would have to consider similar losses. Or we could consider the vehicle itself as the transmission and the UE or the user equipment. We have to consider then what are the application losses within our application, what we want to, it depends on what we want to achieve. So this is a very generalized sort of form of presentation, but we have to be very clear what we want to achieve with this system. So depending on what we want to achieve, then the losses, the margins, all of this would vary. So if you were to take a very simplistic view to this link budget concept, then essentially we want to maximize our distance between the antenna of one device and the center of the antenna of another device. So we want to get this Dmax. So then on a vehicle, perhaps in one direction at position P1, we would be able to get a maximum distance of Dmax 1. And after this, we don't get any reception due to different effects from the link budget. Perhaps we don't have sufficient power in the system. So meaning that we get a distance of Dmax here in this direction and no signal behind. But considering a different direction on the same vehicle, if the device is at the center of the vehicle, then we might have another distance Dmax 2 at a different angle, perhaps at P2. And then similarly, perhaps in another direction, due to different effects, orientations in the vehicle, orientations of the device, the directionality of the antenna that's used, things like that. So what happens then is that if you were to look at it from a perspective of the entire vehicle, we have to be careful to understand that we would have different losses, different ranges expected in different angles around the vehicle. And this is really important when you're doing applications for wireless communication that are very close to the vehicle. Okay. This also has an effect for far field and very long distance measurements as well. And it can be more pronounced, but it's more relevant when you're talking about closer to the vehicle. Another aspect to consider when trading off constraints is the methodology that we are using for the particular function and its usefulness to us. So for example, in this case, you're talking about two-way ranging using ultra-wideband, where the clock information is transferred from unit A to B, and we know the time of transmission. Therefore, we can calculate back what is the distance. But if there are clock inaccuracies between unit A and unit B, then we try to eliminate it by doing a second communication back so that we can equalize the losses, and then perhaps a third. So then the question is, how many times should we make this transmission up and down to reduce or to maximize our accuracy? There's also the aspect of, because you're doing this ranging so many up and down cycles, in case an attacker starts to add in a signal. So that's where we call it secure ranging. So we have to really be careful about what we're trying to attempt, and because there's also a certain amount of energy that we will use in doing this, and you're going to do this multiple times a day. It's not just once or twice. So then we would have to be careful about the energy budget that we have as well. Similarly, we have limitations in terms of application for wireless, in terms of range, and also in terms of coverage. Now, for example, in terms of range as well, as we saw before, we could have range differences in different angles, but we could also have range differences due to the use of different devices, different orientations of the device in the vehicle. So we have to be very careful about what kind of range we are getting, what kind of function, using what kind of wireless technology. But another point also to consider is, where are we positioning the device? So for example, here, if you position the device here, we only have a coverage in this direction. So if you were to be standing here, for example, we can't really do any ranging because there is no wireless signal there. And this would then give us good justification to have multiple transceivers around the vehicle. And this is one of the reasons why we do this. So if you were to consider an actual vehicle like this, this is what it would look like from a finished perspective. But if you were to look at where we want to position our transceiver, then we are limited to positions where we can actually attach the transmitter to the body. So then we would be limited by where these trusses are located. We also don't want to be blocked by metal on all sides. So then we are also limited by positioning. So if we position our transceiver at the bottom of the vehicle in the center, it would look something like this, and it would be blocked on all sides by the metal doors, for example. So that really limits our utility in this condition if you want to communicate outside the vehicle. If you want to communicate inside the vehicle, then if somebody is actually sitting on top of the transceiver on the seat, then they would be absorbing the signal, and then they reduce the amount of signal that is available to communicate. Similarly, if you want to place it in the front, close to the dashboard, there's a lot of space to put a lot of electronics there. But then when you actually look at it from a real perspective, there's actually also a lot of metal blocking on all directions. So we're again limited to which directions we can actually communicate in. So you can have an estimate of this performance from just viewing it, but you also want to do measurements, because sometimes the metal can act as a reflector, as a waveguide. So you might get signal in areas that you didn't expect to get there. So you want to do this measurement to ensure that you understand where the coverage is and is not. Yeah. So similarly, the best position then would be right on top of the vehicle. You would assume to put it right on top of this truss, because it's right, this is the highest position in the vehicle, so you get the furthest reach. This is right in the center of the vehicle, so it can see all around the vehicle. But then, as you see, the aesthetic effect, there's glass here. So if you were to put an electronic item here, it would really block the view. So aesthetically, it may not be the best position to use it as well. So we have a lot of constraints just in terms of where we can position our transceivers when talking to our OEMs. So it's really important to understand what the body type is, what's the vehicle aesthetics that they want to present, and things like this. Another important trade-off when applying wireless communication on the vehicle is the availability of the technology. So different technologies define different pulse rates. So in this case, I've taken the example of ultra-wideband low rate pulse and ultra-wideband high rate pulse. In terms of accuracy of positioning, they both have pretty good positioning accuracy, but due to the longer interval between LRP, therefore you would have better availability of the HRP standard. So in this case, you have more signal being sent at a given time. So therefore you have more possibility to have a faster response, for example. But there's going to be a trade-off in terms of energy utilization. So that's always going to be our problem with wireless, the trade-off between utility and energy efficiency. So here you also get a feel of functionality versus efficiency. For example, if you were interested in having precision distance measurement using ultra wideband low rate pulse, we still have a very high accuracy. High rate pulse, we also get high accuracy, but perhaps we want to use BLE, for example, because it's a lower energy utilization than even the LRP. But then the accuracy here would be quite low. So we have to be a bit careful in terms of how we are balancing out the different features in terms of which technology we use to do which application. So here, everything is pretty good in terms of secure engine. But in terms of current consumption, this is very high. So we have already done a trade-off in terms of utilization. Another very important part in terms of selecting a technology to have a feature is the spectrum occupancy in that spectrum. And this is usually a big problem for us, is that if you were to select, so what you get to see here is the spectrum occupancy can vary over time, can vary over frequency, and it could have different intervals depending on what's the feature that's being used. For example, so here you see the spectrum occupancy increases very high at 12 p.m. or 12 in the afternoon, and it could be very low in the nighttime. So then you already have a utility here to use this technology if you have an application that only works in the night, for example. So you also want to be able to use areas of the spectrum that are not heavily utilized, so that you have the availability of your feature all the time. So the robustness, the reliability increases. Because if there's a lot of other communication occurring in your spectrum, then your signal could be lost, there could be collisions, there could be too much interference, so therefore small signal to noise ratio. This could affect the function as well. Similarly, you also have a constraint in terms of, as designers, we want to design our product in a good, pristine environment that ensures that there is no variable noise sources coming in and going out, and we want to ensure there's no reflections in our system. So for example, you use an EMC chamber or an anechoic chamber to do your product development. But in the real world, there's going to be a lot of, it's not going to be a shielded room. There's going to be reflections from all over the place. The floor is going to be made of concrete, not ferrite. There's going to be electronics that are going to be emitting signals of varying strength, varying response, for example. You're going to be charging your vehicle at different times. You could have different charging mechanisms. So there's a lot of aspects that would be completely different from your design environment. And this is another big constraint as well, that your design might be perfect in a design environment, but may not work in an application environment. So this is really important to understand what different features could affect the application. Then, of course, something we call coexistence. A lot of different countries, because there's going to be certain parts of the spectrum that cannot be used because they are restricted for military use, for example, and different countries allow different bands of the spectrum to use for different products. So in those, what that means then is that everybody who wants to use, every standard that wants to use that band are all in the same band, essentially. Yeah, so for example, here you see that LTE band 40 is very close to WLAN channels 1 to 13, for example. So then somebody communicating on LTE band 40 would be using a signal that could possibly interfere or very close interference to the WLAN channel 1 to 13 if it's being used. So of course, in Wi-Fi 7, there's a lot of sensing that is being done so that the router could use a different channel and then communicate to the device to shift channels and things like that. So this is some of the mitigation efforts that are currently being done on some of the newer standards. But in the older standards, we still have this restriction, especially in case BLE also operates in the same band here. So there is strong potential interference for LTE band 40 into the BLE spectrum. Yeah. So, but of course, BLE as well uses multiple channels, so it's able to select a channel that then doesn't interfere. So similarly, you also have issues with satellite communication. Certain spectrum are allocated for different services, and you then have to be able to use a standard that does not get affected by another standard, for example. And as we see here in the future, Wi-Fi 7, ultra-wideband, high-rate pulse, 5G NR, radar, 4G LTE have very strong potential to interfere in the band between 5 gigahertz and 7 gigahertz, for example. Of course, all of these standards are now slowly becoming more and more intelligent in the sense that they can utilize different parts of the spectrum depending on what kind of noise is available. But nevertheless, the problem still remains, or rather it's an aspect that we need to keep in mind, yeah, something that we need to consider. Like, for example, here our radar DFS is specifically designed to have a dynamic frequency selection in the utilization of radar. So therefore, if the band is being used by Wi-Fi, for example, radar would then shift its frequency. But in some countries, it is actually banned from being used. So USA and India do not allow Wi-Fi and 5G systems to use the C-band radar band. Yeah. So that's another point that has to be very careful in terms of which countries, which destination is your product going to, because there will be different requirements. And then, of course, you have interference, just standard interference, noise sources affecting your application. So here you see a GPS signal affected by CW interference. GNSS signals are also very close to some of the LTE bands, and potentially LTE can overpower the GNSS in these bands. GNSS is our global navigation satellite systems. And then, of course, this is usually the last aspect to consider, but usually the most expensive and the most important, because depending on where your product is going to, you have to meet the regulatory requirements of that country, which defines which frequencies can be used, how much power can be used, how often can you use that wireless communication in that country. And usually what this means is that a design that may be really useful and really efficient and really cost effective in one country may not be allowed in another country at all. So then redesigning that would take significant efforts and would increase the cost significantly. So you have regulatory organizations like the ETSI in Europe, FCC in US, ARIB in Japan, SRRC in China, Anatel, Brazil, ENACOM in Argentina, ISED in Canada, NTRA in Egypt, and so on and so forth. There's a lot of different agencies. Right, so that's just a sort of basic overview of the common constraints. There's a lot of other constraints as well. So we have to consider range versus function in terms of what is the propagating part, the fading effects. We also have to consider what is the function we want to provide versus its availability. So the reliability of service, is it going to be a high reliability system or a low reliability system? Then in fact, we also constrained by a lot of times the receiver sensitivity. So when you take a particular receiver with a particular sensitivity and actually place it in a product, you will see that the system sensitivity starts to degrade because of maybe the grounding is different, the board is limited in terms of its grounding, in terms of the interference from nearby electronics. So having a perfect system using, the receiver sensitivity data may not be in reality possible. So you have to consider the system sensitivity effects. Then, of course, transmit power versus available power. Yeah, perhaps we want to transmit at a peak power of a certain dBm, but the amount of available power in the system is not sufficient. Then we have to balance this out as well. Then in terms of link budget, how much of the budget is allocated to margin? Because margin is a sort of waste of your budget. Yeah? So then if you don't have enough margin, your system starts to degrade in terms of reliability, because in the worst case, there's not enough power. So then it doesn't work. But if you allocate too much margin, then you're limiting your application in terms of how far it can be used and things like that. Then, of course, you have operational characteristics versus coverage. Yeah? So where do you want your function to operate? As you saw, there's zones where your wireless doesn't communicate. So then if you want to have a distance measurement in the area that doesn't work, then it's not possible. Yeah? So we have to balance out the operational requirements versus the actual coverage on around the vehicle. We also have different AGC effects. AGCs affect the phase on the transmitter side, but also on the receiver side, for example, and how important is phase information in your application. In case you're doing AOA, will the AGC affect your AOA? So then you have a very limited dynamic range. You start to fail when the AGC takes over, for example. Then you have frequency versus distortion. This is really important, especially in wideband or wide spectrum communication systems. Your distortion in the leftmost channel may be completely different from distortion in the rightmost channel because of nonlinearities in your transmitter design, receiver design. Then, of course, the RF antenna. Ideally speaking, you would have a point source antenna that would have an omnidirectional profile, but in reality, you can never implement an antenna like this. So then whatever antenna you implement would have a directional profile. It doesn't have signal in all 360 degrees. Then this limits where you have the best coverage, for example. And then, of course, interference robustness. This is becoming significantly more important because our devices, if they are not able to withstand interference, co-channel or adjacent channel interference, then it starts to fail again. So then how much shielding do we want to add? How much grounding do we want to improve? Is it a multi-channel system, a single channel system? Things like that. And then, of course, there's a lot of other aspects that would be specific to some of the automotive, some of the body constraints as well, some of the application areas that we want to consider, or just some of the functionality that we want to provide. Right. So that sort of comes to an end. Yeah, so this talk is meant to give you a sort of insight into some of the issues that we see in industry. And primarily, the reason why we use wireless communication, because it's typically more constrained than a wired system, because you have signal integrity issues, you have coverage issues, you have a lot of different problems that you wouldn't see in a wired system. But then, of course, the key thing is you're eliminating the wire, reducing the cost significantly, and you're able to just connect anywhere without plugging in, plugging out, things like that. So the cost of installation starts to drop. You also have a lot of features that you can implement in wireless, like especially when you're using wireless sensing that you could never do using a wired system. And then, of course, you have a lot of constraints in terms of the functionality. So we also need to consider which technology we're using for which functionality of the wireless application. And most importantly, usually in most applications, except if you're working for Apple, for example, but cost is very important. Cost is always going to be a concern, and you need to balance your cost versus what utility you're getting. And then, of course, in most applications, quality of the service is really important. And then, of course, reliability of the service. How often is it available? How do you really have it when you need it, kind of thing? The worst case performance, things like that. Right. So I think I'm on time. So 45 minutes. Any questions?
I have a general question. Like, I feel that like most of the applications sort of wireless that you showed for automotive are mainly driven by like regulatory constraints, like for example, type of institution, secure, so do you like envision like wireless applications applications to go beyond these regulatory requirements to more like user experience or application oriented in the automotive sector?
Yeah, absolutely. Yeah. So typically in the automotive sector, we are really constrained by the fact that the governments are looking at us very closely because, traditionally the automotive sector was this huge metal lump that was moving at high speeds, carrying people inside that. So safety was a very critical aspect, and governments are very closely monitoring automotive industry for safety aspects. And because of this, we are very highly regulated industry. And therefore, if you were to, think about in a very sort of Tesla kind of way, where you just put autopilot straight off. If you were to go to Germany, it's bad. So you can't. So regulatory wise, we are really critically, constrained, and we really need to meet regulatory approval. But nevertheless, in certain regions of the world, it is a little bit lax. So I would say in terms of regulatory aspects, we would be concerned of where we are using it. But in terms of functionality, typically, it's mostly cost in the automotive world. So new functions are always respected by our customers. They're always looking for innovation. But of course, the cost to them is always a concern that they bring up. Hope that answers your question.
Hello, Brian.
Hi.
Hi. So nice. Thank you for your nice talk. I have one thing. Understanding. You had already pointed out all the point related to wireless communication, but how about the effect of this much of wireless signal into the car space to the health of a human being? So because there's too many wireless signal, does that affect on the health also?
Yeah, that's a very good question, and it's often asked by our customers. Yeah, so there's very clear regulatory requirements for how much RF power we can use, and typically that's defined in something called the specific absorption rate (SAR) requirements. So different countries have different requirements, and typically our power levels are much lower than what would really affect human tissue or human beings in that sense. So typically not too much of a concern in terms of what we are currently using. It is definitely something that is verified on the vehicle by all of the OEMs, depending on which country they're going to. So in terms of regulatory compliance, they are always meant to be designed to be compliant to regulatory requirements. But nevertheless, what we don't know, we don't expect. So if there are aspects that are unknown to us, then whenever it does occur, then there's a very strong regulatory push to ensure that it is safe, to ensure that it is not affecting human beings. Yeah.
Thank you. And one of the thing which I also wanted to understand, when you say wireless sensing and explain the welcome zone, right? So I understand that if some people will come near to the car, it will automatically open it, right? But how do car know that the same people is coming, or someone else also can come, right?
Right. So typically, this is one of the reasons, especially in the design of our systems with access, we are identifying the position of the user device, not the user itself. So the device is unique, and that device can be shared between different users. So for example, if you have a device A and it is used by user A, then the car would be looking at the device itself, not the user. Mm-hmm. So if device A was given to user B, then the vehicle would authenticate device A, not user B. Yeah, so wouldn't be looking at which user is being used, is using the device. So it's mainly device based. But future systems, we are looking at camera based systems for facial recognition and things like this. Yeah. But typically device authentication is much more accurate, much more reliable. But of course, who is holding the device is always going to be a question mark.
Okay. One thing I wanted to understand in terms of when you say the user, I mean the device positioning, right? So in terms of this space, then automotive space, what is the accuracy of positioning you are looking for? Like in millimeter, a centimeter, or meter range, or like how much is the reasonable amount of accuracy you think this much of accuracy if we attend by a system is reasonable to opt for this type of application?
Yeah, absolutely. I think that's a good question. Yeah, so that is really dependent on what we want to achieve. Yeah, so in terms of this inside-outside detection, we actually have a requirement from our European regulatory agency that uses a standard called something called the TACHM standard. Yeah, and here we are required to be within centimeter accuracy in terms of our positioning of the device inside or outside the vehicle. And that means we are not allowed to allow the engine to be started if the device is outside the vehicle, and only allow engine start if the device is inside the vehicle. So in terms of that, we have to be in terms of centimeters accurate, but it depends on what we want to achieve. For example, if you want to do welcome lighting, that means the vehicle lights up when the user is approaching from a distance of 10 meters, then 1 meter accuracy is not really an issue. We don't really need centimeter accuracy. So meter accuracy would be sufficient to achieve this. And then if you were to do something like, we want to switch on the air conditioning of the vehicle in a very hot climate, for example, or the cooling or the heating function in a very cold climate, and the user's position, maybe the car to the house is maybe, I don't know, maybe 500 meters away, then we don't really need high accuracy. So it depends on what kind of functionality you want to implement.
Okay, thank you. So I mean, just to further on the explanation you give, so the system inside the car and outside the car would be different system for the positioning, correct?
It depends, yeah. So we use positioning for different applications. So it doesn't really mean that we need to have a certain accuracy for positioning. The accuracy for positioning would depend on what function we want to achieve. Yeah, so it depends on what is our feature that we want to provide.
Okay, thank you.
Sure.
Any other questions?
Hello.
Yeah, sure.
Hello. Can you hear me?
Yeah, so I think typically if different standards coexist, it's a challenge for us. Yeah. But the reason why they coexist is because different countries would allow them to be used, or would allow users or allow standards to use certain parts of the spectrum openly for certain standards. So therefore, that means anybody who has a wireless technology that they want to implement is constrained into that band of spectrum. So that's usually why you have so many different standards operating, because you have a lot of different functions. You have technologies that would give you long distance communication. You have technologies that are very good for short range, very high efficiency. You have wireless technology that give you a lot of bandwidth, for example, but very short range, or things like that. So they would all be sitting in the same band of spectrum. And that's where the issue comes in, which we call coexistence. That means that there should be a certain level of investigation by these standards organizations and by the industry as a whole to ensure that certain standards don't interfere with each other. And as the standards progress, they implement technologies that allow them to sense and prevent them from interfering from each technology. So that's typically what you're seeing in the industry today. So it's definitely a challenge more than a benefit. But the benefit is, of course, you have so many different features, that you have so many different technologies. You can communicate short distance with power, or you can try, communicate long distance with high bandwidth, for example. Sorry, there was somebody with a question online.
Yeah, can you hear me?
Yes.
Hi, Nicholas Wong here. Thank you, Brian, for the talk. So I wonder if you can comment on a practical problem. So sometimes when I'm driving, I use my phone as my GPS. Okay, Google Maps or something on my Apple phone. I connect to the onboard infotainment system through CarPlay. And then when I go into a tunnel, especially the MCE, my GPS signal cuts out. So I'm wondering, how can this problem be resolved? Now, I know it's not something that only concerns the car manufacturer. There are GPS satellite signals involved, and there's also handset manufacturers involved. So part of my question is, whose problem is this to solve, and how does it get resolved?
Right. Yeah. So that's a classic application issue. It's typically we call it shadowing, meaning that the user device, the utility device, is in a region that is not able to receive a signal. Yeah. Then it's because GPS signals are coming from satellites that are in high orbit around the Earth. Yeah. Depending on which user, it could be low Earth orbit, could be high geosynchronous orbit, for example, or it could be orbits that are changing frequently. But because the signal is so high up, it is literally or virtually vertically above us, and that means any blocking effect, like a tunnel where there's a lot of stones or material to block a signal from passing through it, would then have this region under the inside the tunnel as being a shadow region. Yeah, so GPS is a very critical feature that is used by a lot of different applications, and is in a lot of countries also considered an essential feature. Yeah. So typically in cities, a lot of countries, the tunnels have GPS repeaters, so that this GPS signal is received from the satellite and then sort of directed into the tunnel. So there's GPS repeaters in a lot of or GNSS repeaters in a lot of these tunnels. So yeah, in case, for example, you still do see some shadowing effects, it could be temporary if the car is moving very fast, but it could be also permanent if your car is stalled in a tunnel. So nevertheless, I think this issue would still occur, but typically to mitigate this, most tunnels have GPS repeaters inside them to allow you to continue to receive the GPS signal and continue to do positioning. But of course, the positioning starts to become slightly inaccurate as you go deeper into the tunnel.
Okay, so there's not really much you can do to improve the design of the automobile. It's more for the urban developers to put repeaters in the tunnels, is that right?
Absolutely, yeah. There's very little we can do on the automotive side, because at the end of the day, GPS is designed as a function that there is a very high power transmitter high in the orbit, and there's a very high sensitivity receiver in the device. And that high sensitivity receiver receives signals from at least 3 different satellites, knowing their position in the sky, knowing their time of flight, and then makes an estimation of what the position is on the Earth. So what this means is that the signal should be in terms of time of flight accurate. And this is where the repeater starts to affect its time of flight. And yeah, so this is why the positioning starts to become slightly inaccurate, but there's not really something we could do on the vehicle side, on the receiver side, because it's very passive. It's just receiving the signal. But perhaps there are ways in which the GPS signal can be, there are what they call localized transmitters, where there's GPS signals not coming from a satellite. They have a fixed position in a city. And this, of course, is then, how do you say, implemented by urban planners, and yeah, would be an improvement in what we see.
Okay. I wonder whether there could be an application for cooperative communications between vehicles to solve
Absolutely, yeah. I think there's no limitation there.
Okay, thank you.
Thank you.
Yeah, any other questions? So we can have it, we can adjust sometimes. So thank you for our speaker today. Like
Brian Fernandes, for coming down to NTU and supporting IEEE and NTU IEEE GSC for the industrial talk. This is our first talk. So let's thank our speaker today. The session was very interesting, very informative. So for all the audience here, thank you very much for coming for the talk. And we have ordered some pizza for everyone here. So please help yourself. Maybe for now we can have a group picture first and then get pizza out.
So we stop the recording? No.